Okay, so what we just talked about, we can break down a little bit further and we can say that when the sum of the forces equals 0 newtons, we can have two situations. The first one can be no movement. The second one is a little bit different. Let me ask you this. Can a body in motion be in equilibrium? Yes. Good. Who said that first? Grace, why did you say yes? Okay, so think about this. So I can have some movement. But if I have some movement, there are some conditions. The first one being there is no acceleration. Or I could say that as moving with constant velocity. Now I want you to stop and think for a minute. When I say constant velocity, and I don't want you to tell me, I want you to think about this for a minute. When I say constant velocity, what does that mean? There's two things you should be able to tell me about that. What is velocity? What's a good short definition of velocity? What do you think, Camden? A magnitude with a direction. What do we call that magnitude? Speed. We call it speed with direction. So this means I have to have constant speed and unchanging direction. So there will be instances where I have force equilibrium, but I have motion. And again, we call it static equilibrium. So that's just another name for it. Now, before we move any further, let's talk just a little bit about free body diagrams before we actually start drawing them. So they're used in all force problems. It doesn't have to be motion. It doesn't have to be something sitting still. Anytime a force is applied, like when we move a little bit farther along, we start dealing with coefficient of friction and some things like that, we can still use force diagrams. They're going to represent only the forces, I would say, on the isolated object within the system. So I'm going to have a whole system that has a bunch of different things going on, and I'm only going to pay attention to one part of it. We say that the object is singled out, or it might say freed, from the system. I'm just giving you that stuff to kind of give you some of the different ideas of how it could possibly occur, or come to you and see it in like multiple choice questions and those kind of things, or how to work through something and separate it into its parts. So let's say I'm going to make a system. It's going to be a little system. Actually, this is the whole system, my whole desk with all the junk on it. I'm going to single out the book. That's all I'm going to worry about. So if I were to represent that, I would have to show my table in which the book is resting on. but then I would only show the book. And in most cases, I would show my point, called point mass, in the center. That's kind of in the center. Maybe I need to make it a little bit bigger so it's more in the center. Now, that dot, we call it the center of mass. And sometimes, not usually in these force diagrams, but later on, you might see it as center of gravity, because remember, gravity acting on the mass makes a weight. So those terms are kind of interchangeable. This center of mass is considered to be a location. And it is where we say all the mass is concentrated. So I'm going to maybe call this a point mass. If I have an object like that book, and it has what we call constant mass density, then the center of mass equals the center of the object. So what does that mean? Basically that means any normally shaped object, like that book, where I could have had a block of wood or, you know, normal shapes, then their center of mass is normally located in the middle. Then you can have weird things. Like my eagle that can balance on that little tiny tip, because its center of mass is not located at the center of its body. We're not going to worry about that right now, but we will later on. But do you see the difference in how this book balances? This doesn't necessarily have to be up here. But I do the same thing here. And the bird balances. By looking at that different motion or non-motion, lack of motion, I can see that they have different centers of mass, and I can see that they're located in different points. What part of this bird is resting on this pivot? Its beak, right? So if I were actually drawing this, it could be a block, but its center of mass would be shown at one edge. And that's all you need to understand about that right now. We'll look at center of mass mathematically later on. Okay, so back to my book on the table. I'm going to ask you some questions about it. I'm going to go ahead, I'm going to put that drawing up here at the top so I've got it to work from. Okay, so I've got my book on the table. What's it doing? But absolutely nothing, it's just hanging out. Are there any forces acting on it? Yes, can you tell me what they are? Tell me one, Ellen. Good, gravity. Very obvious one. How's gravity acting? Down. So I'm going to show it. in the direction it's acting. Is there anything acting on that book besides gravity? Any push or pull? Anything else acting on it? Oh, Amelia. Yeah, now wait a minute, you're absolutely right, thank you. If this has no other force acting on it, only gravity, what should it be doing? It should be moving down, right? Is there a force acting on this book now? Yes, how many forces? Maybe at least two. Me and gravity. If I let go of it, what force is acting on it? Just gravity when it falls. So now that tells me it's not falling. There has to be something else acting on it. Amelia hit it right on the head. The normal force. The normal force is equal in magnitude but opposite in direction to the force of gravity. And it's perpendicular to the surface. And because that book is not falling, and I didn't do this with a ruler, but you will tomorrow in lab, this force shown should be equal in magnitude and opposite in direction to this force. So I should set a scale and I should follow it. Don't forget about it. You really have to think about what's happening. I'm going to write that up here. So discuss it tomorrow with your partners. What's happening here? There are some things I'm going to tell you something to do, and other things they'll just be sitting there and you have to figure it out. So think about what's happening. Then you get ready to do your diagram. You're going to set a scale. You're going to follow it. You're going to be sure that you represent all forces, both magnitude and direction. And in our book on the table example, you guys told me there was no movement. What do I call that? No movement. What's it called? What has to be true about my FG and my FN? And what do I call that? Someone has to know the answer to that. Camden? Yep. So this is static equilibrium. So I would say my forces are equal in magnitude opposite in direction. And then I want to talk a little bit about both the forces. Let's look at gravity first, or F sub G. Really, what is F sub G? Force of gravity, right? So it is the force of gravity acting on this mass. Gravity has to act on something. So we can call this Fg a force acting on a mass. It would be a mass, not a mass. Force acting on a mass where I have the force of gravity, G, acting on M. Or G times M. What is that? Do you remember from before? Hey, good. So this FG really equals the weight of the object. Or we have that old formula, W equals mg, which when we learned that, I said we measured in newtons. We'll talk about newtons later. Now we're going to start thinking about newtons. Does Fn equal the weight of the object? Does Fn equal the weight of the object? What do you think, Braden? I think it does. In what way does it? Good. So the force would be equal, the direction would be opposite. So yes, they equal each other, their sign's different. All right, so let's look at something else. Let's look at a free body diagram number 2. And I'm going to change this. Let's see. No, I'm only going to do one thing to it. So I'm not just using my hand. I'm just going to place this box here, and you're going to have to trust me on this. I'm applying force. Is the object moving? Is the object moving? No. But I do have an applied force. So I have to diagram that differently. And I don't worry about that box. That's just the medium through which I apply the force. So I would once again show my book on the table with a center of mass. Is gravity still acting on that book? Yep, so I have to show it. Does that book still have a normal force? Yep, it's not falling through the table. So I show my Fn. Then I have to stop and think about the direction in which I applied the force. I was pushing this way, yes? So if I had motion, I'd be going this way. So I'm going to show my applied force. And when I was doing it the way I wanted to, was it moving? No. So what's that force that stops things from moving? Friction. So I have to show that as well. Equal, but opposite. I show my F sub F. This F at equals an applied force, I'm going to say, on one object by a different object. It could be a wall the car slamming into, whatever. If I were going to take this and make it a point diagram, I would simply draw my point, draw in my FG, be sure that my Fn is equal to it, my applied force, and my frictional force. So it essentially looks the same without the box. This frictional force, we will say it is parallel to the surface on which the object rests, and it either prevents movement or slows movement. So it serves two purposes. Depends on what's going on. We're going to try to do one more really quick. I'm going to set up something that looks a little different. Let's, okay, let's say I have that. What have I changed? What did I just do to that? Now my book is what? Is it moving? No. How's it different? How? I changed the angle. It's on an incline. So I've changed the angle. So let's look at that. And the first thing I want you to remember when you do these kinds is an incline does not change the direction of the force. The normal force is still perpendicular. Gravity is still down. The way I draw it looks a little different. I have to show a little more of my system. I show my tabletop. I show my board with my angle, whatever that is, you can figure out when you need it. I show my book, and I show my center of mass. So let's do our FG first. What's the direction of gravity? Yes, down. So I'm going to draw it straight down. The force is down, but it's part of a triangle, right? When I look at it compared to the surface. So I still have an X and a Y component and an angle. So this FG can be broken into components when I'm dealing with an incline, mathematically. I also have to show my normal force, which is perpendicular, so I'm just going to eyeball this. I'm going to be coming off there. That's not quite enough. I'll make it fatter. It's a fat arrow. So there's my normal force. What other force has to be acting on that board? Or on that book, I should say. See if you can answer that. What other force has to be acting on the book? Amelia, what do you think? Friction, why'd you pick that? Because it's not moving. So if it's moving, because of gravity, which direction? Well, no. Because of one component of gravity when I solve the problem, which direction is it most likely going to move? This way, right? Okay. So friction then would be opposing that motion. So I would show it coming out of here. That's the direction of my friction. So my Fn is equal mag, we say opposite direction, and we'll figure that out mathematically later on, to, in this case, we say the components of Fg. And then my frictional force still is just a force that prevents or slows motion. Stay here for 1 second. I'm done recording, but what I want you to do for homework is that handout that you picked up. Gretchen, I'll post that after the video. I want you to do 1 through 4 on the first page. Is there 4, Emma? Can you look at that for me? 1 through 4, and then if you flip to the back, I think it's 3 and 3. So what we're going to do on the back of that page, let's do 2 and 3. So 1 through 4 on the front, try 2 and 3 on the back, and then we'll pick up tomorrow, talk about it, and move over to lab.